Hey guys, so here's the video for our next section, which is 4.7, and it's on L'Hopital's rule. So L'Hopital is just some math dude. I used to call this L'Hospital's rule. Anyway, it's another one of those theorems that we have. It's actually kind of just a tool for calculating a limit, so we're actually going back to limits for this section, like we did at the beginning of the year. So if you guys remember, before, if we had 0 over 0 or infinity over infinity, that was bad news, and we had to simplify using algebra. Excuse me. Okay, so I'm going to introduce L'Hopital's rule, which will allow you guys to avoid the use of algebra. You'll be just using calculus, so derivatives, instead, so we'll write that out and then we'll do a couple of examples. So this is definitely cheat sheet material. And again, it's called L'Hopital's rule. And basically it says that the limit as x approaches alpha, and note alpha could be plus or minus infinity, it could be 0, it could be any number. It's just kind of a placeholder. So the limit as x approaches a of f of x, oops, actually my pen died. Thriving. Anyway, before I write this, it is important to note that this only works for functions in the form of like a function over another function in fractional form. So we'll have some function in the numerator and some function in the denominator. So again, like I said, I'm going to call these function fraction limits. That is not a technical term in any way, shape, or form. But that's a good thing to remember. So the limit of f of x over g of x is the same as the limit as x approaches alpha of f prime of x over g prime of x. So if we take the derivative of the top and the derivative of the bottom, the limit as the original function will be the same. Now, I do want to point out one thing so that you guys don't get confused. This, oh, is it going to let me? This right here is not the same as the derivative of our original function, because remember, the derivative of a function over another function requires the quotient rule, which is low d high minus high d low over low low, which is not what this is equal to. This is just taking the top, taking the derivative, taking the bottom, taking the derivative, and leaving them in their respective spots. So this is not the derivative of this guy. It's just that these two limits are equal to each other. Okay, so now we're going to do a couple of examples, because I know that just a theorem in and of itself is kind of confusing sometimes. So we'll do 2 or 3. Example 1. Find the limit as x goes to 0 of the square root of 9 plus 3x minus 3 over x. So note, just plugging in gives us 0 over 0, which is bad. So normally we would do algebraic simplification, but we have this new handy dandy tool, So we'll use L'Hopital's. So according to L'Hopital's, the limit that we're looking for, I'm going to rewrite the square root of 9 plus 3x to 9 plus 3x to the 1/2, just because it's easier for derivatives. Minus 3 over x is equal to the limit of the derivative of the top over the derivative of the bottom. So if I take the derivative of the top, I'm going to have 1/2 9 plus 3x to the negative 1/2. The minus 3 goes away, and in the bottom we're going to have 1. So now if we plug in, we're going to get 1/2 times 9 plus 0 to the negative 1/2, which is equal to oh, I'm missing something, guys. I forgot to use the chain rule. Okay, so back here, after I'm done taking the derivative of the outside, I need to take the derivative of the inside, and the derivative of 3x is 3. So then I get 1/2 times 9 plus 0 to the negative 1/2 times 3, which is equal to 1/2 times 1 over 3 times 3, which is just 1/2. Okay? So that's a lot easier than dealing with the algebraic simplification of the square root of 9 plus 3x minus 3 over x. I think that would involve a lot of conjugates, and it's much more difficult than just taking the derivative. So that's what L'Hopital's rule gives us. Let's do another example. Example 2. So let's find the limit as x goes to 2 of x cubed minus 3x squared plus 4 all over, this one is long, x to the 4th minus 4x cubed plus 7x squared minus 12x plus 12. And if you plug this in, you'll get 0 over 0 again, which we know is bad, but again, we'll just use L'Hopital's rule. So from L'Hopital's rule, we have that the limit as x approaches 2, I'm just going to copy this, I don't feel like writing it again. Okay, the limit of this guy is equal to the limit of the derivative of the top over the derivative of the bottom, so we have the limit as x approaches 2. Remember, guys, to write the limit symbol every time until you actually plug in your numbers. I guess it doesn't matter so much now that you're not taking written exams, but it is good practices. So the limit, or the derivative of the top is 3x squared minus 6x, and then the 4 goes away. And the derivative of the bottom is 4x cubed minus 12x squared plus 14x minus 12. And if we plug in now, we're still going to get 0 over 0. But no worries, we're just going to do L'Hopital's rule again, which we can do. So we actually have, again, I'm going to copy paste because this is a lot to write. So actually, I like how much smaller that is. That's going to save me room. Okay, so this guy is equal to, we had our original limit, we took the derivative of the top and the bottom, but it wasn't, we still got 0 over 0, so we're just going to take the derivative of that top and that bottom. So this is actually the second derivative of our original function. And we have the limit as x approaches 2 of the derivative of 3x squared minus 6x is 6x minus 6 all over the derivative of the denominator is 12x squared minus 24x plus 14. And if we plug in 2, we're going to get 6 in the numerator over 48 minus 48 plus 14, which is 6 over 14, which we can simplify to 3 over 7. Again, you can do the simplification in like Symbolab or something if you're not great with arithmetic. So these are two examples of L'Hopital's rule. I am going to be posting another video because this section kind of includes two different topics, I think, in regards to limits. But before I do that, I did want to talk about one more thing regarding limits, and that is growth rates. So I think some of you are already kind of familiar with this, and a growth rate is basically just how to look at a function, or I guess how to look at a limit and know what'll happen. As x goes to infinity, just based on whether the numerator or the denominator gets larger or faster. I guess larger or smaller. So basically, I want you guys to think about this as like, if we have f of x over g of x, and we're taking the limit as x goes to infinity, if f of x goes to infinity, before g of x goes to infinity, then the limit is going to go to infinity, right? Because if my numerator, because if we have infinity over infinity, that doesn't really mean anything. We know that that's not a legitimate mathematical statement. But if this guy gets to infinity before this guy does, then it's infinity divided by like essentially a number, which we know is infinity. On the other hand, if g of x gets to infinity before f of x does, then the limit is going to go to 0, because if this guy gets bigger faster, we're dividing basically a number by infinity, which we know is 0. If we have 10 chocolate bars and you have an infinite number of friends, remember you get 0 chocolate. So there's just kind of like a handy way that we can represent this, and it is if f goes to infinity faster than g of f, then we say f of x, and then we write these little like less than or equal signs, but we write them twice, and it just means that f of x grows faster than g of x. As x goes to infinity. So that's the same as writing g of x, then two less than or equal or less than signs, and then f of x. Okay, so that's just notation. And then we have like kind of a handy cheat sheet, which is only handy if you're really good at abstract things. So if you don't do well with letters, then this might not be super helpful for you, and you can just go back and use L'Hopital's and the other limit things that we've been talking about. But these are kind of like quick ways to take a limit by just looking at it. Again, this only applies when x is going to infinity. So to set this up, we have to have some variables. So we're going to let p, q, r, and s be positive real numbers. And we're going to let b be greater than 1, so it's also a positive real number, but it just has to be larger than 1. Then we have the following. We have the natural log of x to some power q, so just to some positive real power, that could just be 1, so the natural log of x by itself, grows slower than x to the p, which grows slower than x to the p times the natural log. Here, I'm going to write this consistently. The natural log of x to some power, which grows slower than x to the p plus s, which grows slower than b to the x, which grows slower than x to the x. Okay, so we're going to do a quick example of this. I don't personally think this is super useful because not everyone has these memorized, and I don't know, at that point you could just use a calculator. So just a quick example. If we're taking a limit as x goes to infinity of x cubed over 3x, plugging in yields infinity over infinity, but growth rates, we know that 3x, which is of this b to the x form, grows faster than x to the third, which is of this x to the p form. So x to the third. So we know our denominator is going to be growing faster than our numerator. So the limit as x goes to infinity of x to the third over 3 to the x is equal to 0. And then you would just say by growth rates to clarify that that's how you know how you did it, right? So the 3 to the x is going to infinity faster, so we're basically dividing a number by infinity, which we know is 0. Alright, so that's it for this video. I'll see you guys in the second part of 4.7.